Okay, so the next part of the chapter, we're going to be looking at measurements, conversions, prefixes, scientific notation. So first thing is, the standard units of measurement, I remember learning the SI system was like called the MKS system. So it just kind of made it easy to remember that M for meter, that's our standard unit for length, K for kilogram for mass, or Kelvin for temperature, and then S seconds for time. Then I've got a couple of conversions listed over here just to sort of relate our non-SI system, our English system, to the actual metric system. But the kilogram pound conversion I'll have you memorize. The meter to inches will go a different way, but I'll show you that on coming up. So we are, United States, one of only 3 countries not on the metric system, so we get to learn unit conversions. All right, then the prefixes, for those of you that had me for intro chem, you probably remember kilo, centi, and milli. At least for my face-to-face students, I did have you memorize those. But I am adding 3 more to the list. We're going to do mega, micro, and nano. Those are the 3 new ones. And the way that general chem textbooks, they approach this a little bit differently than how I taught it face-to-face. I'm going to take the milliliter example just because I have it written here. So the way that these textbooks do it is basically when you see the prefix, you can substitute the power. So like 1 megameter is 10 to the 6 meters. 1 kilometer is 10 to the 3rd meters. 1 centimeter is 10 to the negative 2 meters. So you basically swap or, substitute the prefix with the power. So with milli, right, 1 milliliter is 10 to the negative 3 liters, or 10 to the negative 3.001 liters. The way that I taught this in intro was 1,000 goes with the milli, right, and then 1,000 milliliters in a liter. Those are the same, right? A milliliter is 0.001 liters, just like 1,000 milliliters in a liter. Like if I take 1 times 1,000, I get 1,000. If I take 0.001 times 1,000, I get 1. So those conversions are exactly the same. I'm just going to do it sort of this methodology way here, but if you remember this better, 1,000 milliliters in a liter, then go ahead and stick with that. So we're going to practice this down in our first set of practice questions. So for example, the 2.05 times 10 to the negative 6 meters, right? Just recognizing negative 6 is for micro. It gives that kind of curvy U symbol. Really sort of looks more like that, but I think I don't know. Anyway, that's why I write it for the notes. So the next one, 4.03 times 10 to the 3rd grams, right? The 10 to the negative 6 we saw was micro. The 10 to the 3rd is kilo. So this would be 4.03 kilograms. All right, next one, 7.06 times 10 to the negative 9. I remember nano because like our prefixes in covalent compounds, similar, right? The double N, it kind of sounds like it would be a 9. That's how I remembered it. It just seemed like it went together. So we have 7.06 nanoseconds for 10 to the negative 9. And then 10 to the negative 2 is the centi. So 5.15, whoops, I forgot the 1. There we go. Centimeters would be the same as 5.15 times 10 to the negative 2 meters. So we're just, in this first set of example questions, just substituting the power with the prefix. So 10 to the negative 6 is micro, 10 to the 3rd is kilo, 10 to the negative 9 is nano, and then 10 to the negative 2 is centi. Then down here for the next section, what we're going to do is take these measurements. We're going to restate each of those by changing the value. So we're going to put it into proper scientific notation. And then we're going to replace the exponent with the proper prefix like we did in that first section. So proper scientific notation, that's what I was trying to say here, means that there should only be 1 digit in front of the decimal. In other words, your decimal has to follow the first non-zero digit. So if I have 0, let me start with the first example, 6,217, so 6,217 grams. The decimal would be moving 1, 2, 3 spots to the left. So when you move 3 to the left, anytime you go to the left, it's going to be a positive value on the exponent. So 6.217 times 10 to the positive 3. And then what we did here is we replaced the 10 to the 3 with kilo, because that's the appropriate prefix. In the next one, we're going to have 0.0016 seconds. So in this case, we're moving our decimal 1, 2, 3 spots now to the right. So if we're moving 3 to the right, it's going to be a negative on the exponent. So this would be 1.6 times 10 to the negative 3 seconds, and 10 to the negative 3 would be milliseconds, so 1.6 milliseconds. All right, the 0.0717 grams, we're moving now in this case 2 spots to the right. So if we're moving 2 to the right, it's going to be a negative 2 on the power. So 7.17 times 10 to the negative 2 grams. And then that 10 to the negative 2 is centi, so 7.17 centigrams. And the last one here, we've got 3,870 meters. Decimal now is going to go 1, 2, 3 spots to the left. So it's going to be a positive value. So 3.87 times 10 to the positive 3 meters, or 3.87 kilometers, right? Kilo for 10 to the third. All right, now the 0 here at the end, right? We'll talk about why that didn't carry over in just a second. But basically this is a magnitude 0, just like the 0.07. Those zeros in front were just magnitude zeros. The 0.0016, right? Magnitude zeros. Same thing is assumed with this 0 at the end of 3,870. And we'll show how to tell whether or not it is just a magnitude 0 or an actual measured 0 coming up, but we're not quite there yet. So what we were doing here was just practicing proper scientific notation. Proper notation has only one digit in front of the decimal. So you move the decimal to follow the first non-zero digit. If you move that decimal to the left, you're always adding positive to the exponent. If you're moving it to the right, it's going to be negative or taking away. And then we practiced again those prefixes, just replacing whatever that exponent was with the proper prefix, like we did in the section above. Now the last thing here is we're going to go in the opposite direction. We're going to replace the prefix with the correct power and then put it into proper scientific notation. So the first one here, we had 355 microseconds. So first thing I did was I took the micro, replaced it with 10 to the negative 6. And then if I'm moving my decimal to get proper scientific notation 2 to the right, we're going to add 2 to the power. So the negative 6 becomes a negative 4. On the next one, all right, we have 1,885. Kilometer would be 10 to the 3 meters, because kilo is 10 to the 3. And then if I'm moving my decimal 1, 2, 3 spots to the left, right, then I'm going to add another 3. Did I say right for when I got to part A? Anyway, I should write a note. I got distracted. So if I move 2 to the left, it's going to be adding that power of 2. So negative 6 plus 2 goes to negative 4. For the second one here, we moved 3 to the left, so we're adding 3. So the 1,885 times 10 to the third, when we move that decimal 3 spots to the left, we're going to add another 3 to the power. So 1.885, I should have left myself more space, sorry, times 10 to the 6 meters. So 1,885 kilometers is the same as saying 1.885 times 10 to the 6 meters. All right, next one here, 1,350 centimeters. So 1,350 times 10 to the negative 2 meters, because centi is times 10 to the negative 2. And I'm moving 1, 2, 3 to the left again. All of these we're moving to the left. So we're going to be adding 3 to the power. So when I add negative 2 plus 3, overall I get a value of a positive 1. So let me make myself a little room here. 1.35 times 10 to the 1 meters. All right, and then for D, let me write that down here. We had 425 nanometers. The nano is times 10 to the negative 9 meters. And then in this case, I'm moving the decimal 1, 2 to the left. So we're going to add 2 to the power. So 4.25 times 10 to the negative 7 meters. All right, so just practicing proper scientific notation and those prefixes that we want to learn. The next section talks about density. And I didn't put a lot of examples in here about density because I'm sure you all remember this from Intro Chem. But Our formula, of course, is density is mass over volume. We're going to look at liquids and solids for the most part. When we get to the gas chapter, we'll obviously look at the gas densities. And just kind of a quick note, when we look at mass, our unit, right, typically we're going to work with grams. For volume, we're going to be in milliliters. But the unit that is the same as a milliliter is a cubic centimeter. So those are your two common units for density for liquids and solids. For a gas, because they are mostly empty space, the units are grams per liter. But we'll look at that when we get to the gas law chapter. So that's not right now. All right, on the next page, I started talking about densities of solids. So when you're looking at a solid, the mass measurement's going to be pretty straightforward. We're going to have electronic scales. We'll put our sample of our solid on the electronic scale. We get our mass measurement. That's easy. We're done. The volume is going to come from one of two ways. If it is a solid that is regularly shaped, right, we can measure the length, width, and the height. Then we can go ahead and find volume that way. So if you imagine with your ruler taking your length measurement in centimeters and your width and your height using that ruler, right, then when you multiply those together, your volume is going to be cubic centimeters. Alternatively, right, it might be a solid that is not regularly shaped, right, so something maybe that looks, I don't know, like that, little pellets or some kind of nugget, right? And we want to know the density of that piece, and we don't have a really nice math formula for that. Instead, what we use here is the displacement of water. So you would start with your graduated cylinder. Again, my drawing skills pretty poor, and we'd have some initial volume of water. When we put the solid into the water, the only stipulation is it has to be submerged, right? And once it's below the water level, right, the water level will rise when the solid goes in. And then if we measure that final volume where we ended up and compare it to the initial volume of where we started, the volume of water that moves out of the way is the volume that was occupied by the solid. That makes sense. So we just look at the difference in those two volume measurements to figure out what space is being occupied by the solid. So the example I gave here is we've got a solid, we got the mass, right, straightforward from the scale, 25.22 grams, dropped into a graduated cylinder that contained, this would have been the initial, 15.6 milliliters of water. And then after we put the solid in, the volume level rose to 25.0 milliliters. So the difference in those two volume measurements tells us the volume of the solid. Now, we're going to talk about significant figures here in just a second, but I know you probably remember this from intro chem. We've got mass over volume. Our volume is, we're getting it by difference, by subtraction. So we only could measure to the tenths place for both of those measurements, so we keep that measurement to the tenths place. In other words, just one place past the decimal, 9.4. That would be the volume that moved the water out of the way, right? So that's our volume of the water that moved, so that must be the volume of the solid. And the mass was 25.22. So my mass of my solid, volume occupied by the solid. After I divide, I take only two significant figures, and there's my density, 2.7 grams per milliliter. Now for a liquid, the mass is the harder part. Again, kind of going back to those graduated cylinders, we get the volume right from reading the meniscus, so that'll be straightforward. But the liquid, because we can't just squirt it on the scale, what we typically do with liquids is we start with our empty graduated cylinder, and we take our initial mass measurement, and then we add liquid to our graduated cylinder, all right? And when we read that meniscus, that's where we're going to get our volume from. And when now we take a second mass measurement, which is, of course, the graduated cylinder and the liquid in it, right? So both of them combined. So what we'll do is we get the volume right from reading the meniscus. We figure out the mass of the liquid that we added by the difference in those two measurements. So I gave you an example. We've got 15 mils of liquid added to a cylinder. Empty is 156.23 grams. The mass of the cylinder with the liquid in it now is a total of 169.72 grams. So of that 169.72, I know 156.23 of it is just the container itself, the cylinder. So when I subtract those two, I'll get the mass of just the liquid, so 13.49 grams. If I then take that, divide it by the volume that I measured with my meniscus, my mass divided by volume gives me my density. All right. Now the significant figures, right? I mentioned that earlier with the density of the solid, but now we have to talk about it. With significant figures, what we're trying to convey when we give our answers, like we did up above with this density example, not only are we trying to convey the density, but we're also trying to convey how precise we know the density to be. So if you have sort of familiarity with using graduated cylinders or burettes or other equipment in the lab room, there are some graduated cylinders that can only read volume to the tenths place, and there are other graduated cylinders that can read volume to the hundredths place. And the idea with a significant figure is the answer that you get from your calculations, right, cannot be more precise than the measurements you took to get that, right? If you have really good precise measurements, you can have really good precise answers and calculations. If your equipment isn't so great and your measurements thus cannot be that precise, then your answer can't be that precise either. So in chemistry, not only do we want to convey the answer, we want to convey how precise that answer is, or how significant each of those digits are. Were they measured? How precise could that measurement be? So the first rule is easy. If it's not a 0, it's a sig fig. So anything that's not a 0 is automatically assumed a measured digit, so it's a significant figure. The 0 is the tricky digit. There's only 2 scenarios where it will be a sig fig. That's if it is between non-zero digits, or it is after the last non-zero digit and there is a decimal present. All right, so what does that mean? Well, if I have something like 105, there is a 0 between the 1 and the 5, so that is a significant figure. That makes sense that the 1 and the 5 are measured, so the 0 is also measured. The 0.0067, this one only has 2 significant figures because the zeros in front are not significant. They're not measured. The way I think about it is the 6 was the first measurable quantity. Everything before that is just magnitude, right? There's nothing there yet to measure. So zeros in front of the first non-zero digit are just placeholders. That's it. The 20.0 here, now what we're saying is we've measured the 20, the 2. We've measured also the 0 after the decimal. All right, and we'll see this when we practice this in lab, but if we follow the guideline, zeros that follow the non-zero and precede or follow a decimal will be significant. So as long as there's a decimal present. So putting that decimal here is saying that we have all 3 are sig figs. So you have to be careful with zeros at the end. If I just write 20, right, that's only 1 significant figure. If I write 20 with a decimal, that is now saying that 0 in the ones place is significant. It's not just a magnitude 0, it is 20. So this is about 20, this is 20, and if we have even more data on our scale and we write 20.0, that's now 3 significant figures. All right, so you have to be careful with zeros at the end. Now, the 250 with no decimal, kind of like the 20 that I wrote up here with no decimal. A lot of textbooks will say, you know what, that's just really ambiguous. Is that 0 supposed to be significant or not? I follow the rule of the decimal. If the decimal's there, then we know it's a sig fig. If it's not, then we know it isn't. But a lot of textbooks will say, really the best way to convey the exact number of significant figures is to use scientific notation. So you will see more scientific notation in Chem 1 than you did in Intro. And the idea is if I want 250 to say for sure only 2 sig figs, I'm going to write it as 2.5 times 10 to the 2. If I want to make sure it has 3 sig figs, then I'm going to write the 250 that way with the decimal, or 2.50 times 10 to the 2. But when you write scientific notation, one of the benefits is that whatever precedes the exponent is automatically your number of sig figs. You don't even have to think about it. Like if we go back to that 0.0067, right? If I wrote that in scientific notation, it would be 6.7 times 10 to the negative 3. So again, very clear this way, there's only 2 significant figures, all right? So that's significant figures. Now what about operations? When I add or subtract, then I want to look at my decimal places. When I multiply or divide, then I just want to look at my significant figures. And the rule is least always wins, right? Your answer cannot be more precise than your least precise measurement. So we're going to do some practice examples down here. I know a lot of this is a review from Intro Chem. All right, so first example here I did for you. We had 48.2 added to 3.82 added to 48.4394. I got the answer from my calculator. That is way too precise based on the measurements I used to get there. Since we're only adding here, we look at decimal place. The 48.2 only goes one decimal place. That's my least precise measurement. That's going to limit how far I can go for my answer. So it's only going to go to one decimal place. If it helps you, you can line your numbers up this way, like, stack them. Because the idea is, with addition and subtraction, if I couldn't measure what was past the 2 on the first measurement, then I can't really say for sure that that 2 plus 3 is going to stay a 5, right? I don't know, because I couldn't measure that. So you can only go as far in your answer as your least precise measurement allows you to go. So with regard to the decimal place, we'd have to stop here at the 100.4. Now what we're cutting off, that 5, the rule is that if it's 5 or greater, we're going to round up. If the number we're cutting off is 4 or less, we round down. All right, and only look at the very first digit that you're cutting off. So just as an aside, if I had 100.4494 instead, and I wanted to again just go to the tens place, what I'm cutting off is 4 or less, right? A lot of times students will say, well, wait, the 9 would make the 4 go to a 5, and then the 5 would go to make the 4 go up. You don't want to double round. Just always look at that very first digit. Don't look at anything past that. Since this is a 4, we're going to make the previous digit stay as is. So it would just be 100.4 for that one. All right, the next one here, I have 148 grams added to 2.39 grams and 0.0124, and I got my answer from the calculator. And we're only adding here, so we look at how far past the decimal. My 148 grams here, it doesn't go past the decimal at all. So that means my answer is not going to be able to go past the decimal at all either. I'm going to have to stop at the 150. I want to be careful though. I do want to show that that ones place, the 0, is significant. So I do want to make sure and put the decimal in there. Or 1.50 times 10 to the 2, right? Either way. But we do want to make sure that that 0 is a significant figure because we do have that precision. All right, so 150 grams. The next one, again, we're just adding and subtracting. We got our answer, so we look at our decimal places. The first measurement, 15.436, goes to 3 decimal places. 5.3 only has 1 decimal place. 6.24 has 2 decimal places. 8.177, 3 decimal places. So least always wins. We're going to go with 1 decimal place because of the 5.3. So for my answer, just going to the tens place, 6.3, cutting off that 19, so the 3 stays a 3, we would just have 6.3 liters. All right, so with addition and subtraction, just always look at how far past the decimal do we know for sure. Then for D and E, all right, for D, we have a mix of operations. In the parentheses, we have an addition step, and then we have multiplication, and then another set of parentheses with a subtraction. And order of operations tells you you've got to do what's in the parentheses first. So when I add 51.5 and 2.67, I round it to the tens place because of my 0.5. I can only go 1 decimal place there. In the second parentheses, 33.42 minus 0.124. The 0.42 has 2 decimal places. That's limiting how far I can go. So my answer to that second parentheses would be 33.30, 2 decimal places. Now when I go to multiply those two together, I'm going to ignore decimal places now and just look at significant figures. So 54.2 times 33.30 gives me 1,804.86 meters squared. When I look at my sig figs, 54.2 has 3 sig figs. 33.30 has 4 sig figs. Least always wins, so we're going to have to round our answer to 3 significant figures. So I want to take the 1, 8, and the 0, cutting off the 4, The only way to do this one is in scientific notation. So we're going to move the decimal 1, 2, 3 spots to the left, so times 10 to the positive 3. And in front we have 1.80. All right. Then the next one, we have a mix of operations again. So in the parentheses, the first set of parentheses, I have 125.1 minus 1.22. I'm going to keep the precision to 1 decimal place. So I would round that answer to 123.9 grams. The next set of parentheses, I've got 52.5 added to 0.63. Again, because of the 0.5, I can only go to 1 decimal place here, so I'll round that to 53.1 milliliters. So when I divide here, I'm going to take 123.9 divided by 53.1. And when I do that, I want to look at my significant figures. I have 4 significant figures in the 123.9. I have 3 significant figures in the 53.1. So the calculator gave me 2.33333, basically repeating all the way through. And what I want to do is now round this to just 3 significant figures. That's going to limit me, the 53.1. So my answer here would be 2.33 grams per milliliter. All right, and that would convey not only my answer, right, for this must be a density, grams per milliliter, but also how precise I know that density to be. All right, one more example on the next page. We have another mix of operations. So for this one, first in the parentheses, we're going to take 47.5 minus 1.44. We're going to round that to the tenths place. I get an answer of 46.1. And then what we're doing is dividing, and in the parentheses, everything here is being multiplied. So when you're dividing and then multiplying, I don't have to worry about rounding what's in the parentheses here. But I probably will just to make sure I keep track of my sig figs. But technically, if all you're doing is dividing and multiplying, the rule is the same. So just put everything into the calculator and round it at the end to the least number of sig figs. So I'll show you what I mean here in just a second. Let me do the parentheses. I've got 10.5 multiplied by 0.35 and then multiplied by 0.175. So calculator here gives me 0.643125, and that would be meters cubed because I'm multiplying all of those together. Then what I would do next here is I'm just going to divide. I'm not going to round that yet because I would lose some of my information. And multiplying and dividing, it's the same, right? So I'll show you what I mean. I'm going to take my 46.1, divide that by 0.643125, and calculator gives me 71.68124393, right? Way too much information. What I'll do is I'll go back at this point and I look at all of my sig figs. So 46.1 had 3 sig figs, also 10.5 and 0.175. But this 0.35 only had 2 sig figs. So that's going to limit my answer here at the end to only 2 sig figs. So the 71 would have to round up to 72, and my unit here would be kilogram per meter cubed. All right, so that's going to be a good place for me to stop. And in the next video, I'll pick up where I left off, but I'm trying to do just little sections at a time. All right, so that covered prefixes and significant figures.